Okay, as I mentioned in the last video, we're now doing multiple regression. This is something that is going to be useful for your project. But as I said, the book goes over it really quickly and doesn't do it particularly well. If I want to teach multiple regression, it's a very difficult technique to implement because you've got to think about, you know, how many variables you're going to use at once, when you can enter variables, when you can leave variables. And it's impossible really to do it in like a quarter of a week. So this is kind of for illustration and your project, but as I said, it will not be on your exam. Okay, so we had this situation where we have a model and we're going to have y is beta 0 plus beta 1 x plus my error, as we're not doing the hat version. And let's just say that y is my opening weekend. Movie revenue. And we're actually instead of calling this x, we're going to call this x1. X1 is going to be my tweet rate per hour. Now we can get decent predictions, but maybe, before the movie opens, we also know how many screens the movie is on. We may have, we have websites such as Rotten Tomato and Metacritic, and a lot of critics see the film before release. So maybe before release, we also have, an average review score. Now, in fact, we could go on and on and on adding independent variables, but we get to a stage where it's stupid. We could have, what the star has for, the top star has for breakfast, etc. But generally, we want to add some more information as long as it improves our predictive power. So now we have the following equation. We still have our intercept, but we now have 3 different regression coefficients. Now, the intercept is still pretty much the same. This is the value of x. Sorry, the value of y. But this time it's when all x's and let's just take one of these. So beta 2, this is the increase in y when x2 is increased by 1 and all other x's, in this case x1 and x3, are held constant. Now, the regression is, a lot of the things are the same. R squared is the same as the simple regression, but it's, the amount of variation in the independent variable. Sorry, in the dependent variable. Explained by all the independent variables. We have an F statistic, which does basically, it's a little bit like the ANOVA, does an overall test. And we actually have the t-tests, but they are for the individual variables. So t-tests of individual variables. Okay, so that's that's basically multiple regression. And I'll just quickly go through the slides. The slides are just saying the same thing that I said. The betas are the same as simple regression. We can actually standardize our x's if we want to standardize, if we want to standardize our betas, but we don't have to do that. We can have a t statistic for each regression, so each variable. We also have an f statistic that does the overall regression. And the R squared is exactly the same, but it's now the individual. It's all the independent variables. Now, we also have, so generally when we do a regression, we'll look at the overall F test. We will look at the R squared to see how much variance is explained. And then we will do the individual tests on the individual beta coefficients with the t-test. The assumptions are exactly the same as before. We've got a linear relationship. We don't have a curved relationship. And we have this homoscedasticity, not heteroscedasticity, and our errors are normal. So errors are normal and they don't change as our x's increase. Yeah, we don't heteroscedasticity. And we have one additional assumption, and this is multicollinearity. And this basically just says the x's should not be strongly correlated. They could kind of measure different things. So let's just say I have a measure of health. So that's my health. And then we have beta 0 plus beta 1. And then maybe I'll have, amount of exercise. And then we have like the measure of heart rate in the morning. Sorry, that's beta 2. So that's heart rate in the morning. Plus heart rate in the evening. Why did I do the x twice? These guys, people have higher heart rates or low heart rates. So these guys will be strongly correlated with one another. So that would be multicollinearity. And that's a bad thing. It makes the regression very unstable. So sometimes what you would do is you will actually measure the correlation between all your independent variables and check for really high correlations. And if you have high correlations, then you would get rid of one of your variables. So in this case, we'd probably only want one measure of heart rate in our regression. Okay, so let's have an example. I said I'm going to keep this section, as it's not on the exam, I'm going to keep it relatively short and sweet. So here we have some data on condos. And imagine, I think this is old data sets are priced in hundreds. This really should be priced in thousands. So we have the price of the condos, and we have various features of the condos. So we have the price, what floor they're on. We also have a distance from the front office, whether they have a view or not, and these are categorical variables, so no or yes, whether they're an end apartment, whether they're a furnished apartment, or whether they're sold by auction. So let's go back to the data view. So my dependent variable is price, and my independent variable are all of these guys. So this is just like a really simple real estate example. So this sort of regression is used a lot in real estate because towns and cities want to be able to value houses for tax purposes, and real estate agents want to be able to value houses based on recently sold houses in the same neighborhood. So we're going to do analyze, regression, linear, and you see I was just checking this work beforehand. So my dependent variable is price, and basically all the other variables are independent variables. And we're just going to plot the residuals again. We have the residuals on the y, and we can either have the dependent variable or the predicted dependent variable. Let's just do the z prediction. This is just a standardized version of the prediction. And we'll do as we did before with the histogram and the normal probability plot. We're going to click OK. So we have the same data as before. We have the R and the R squared. So here the independent variables account for about 60% of the variation in the dependent variable. So that for a real life example is pretty good. We have the overall test, which we can see is significant. And we have lots of different t-tests. We have a t-test for each of these 6 different variables. And then we have the charts. This actually looks better. Our residuals look relatively normal. They're relatively close to the line. And you see here, there's maybe a few very small, weird ones that have big magnitude and are small here. But here you see the magnitude of the residuals around 0 really doesn't change too much as our predicted value increases. So that doesn't look like we have a big heteroscedasticity problem. So let's kind of go back and let's go back to the results. So as I said, R squared is kind of the same as before, but it's all the independent variables this time. This is the overall test. And I'll just kind of write this down for you. So my null hypothesis is that all my beta coefficients are actually equal to 0. And imagine we have k, we have 6, but we have this is just the number of x's. And they all equal to each other and they're equal to 0. And my alternative hypothesis is basically at least one beta, I will say beta I, we'll have a beta I in the middle of here, is not equal to 0. So all of them don't have to be equal to 0. At least one of these is significant. So this is like, again, it's a bit like ANOVA. It's an ANOVA test. It's an omnibus test. And here we can see that basically we're going to reject H0 if my p-value is less than alpha. And so here my p-value, let's just say my alpha is 0.05. P equals 0.00 is less than 0.05. So we reject H0 and we assume that at least one of our coefficients is significant. Now again, this is like the ANOVA, and I tell this to my boss. I say, one of these things is significant. My boss says, you're an idiot. You've not told me which is significant. So now we test the individual coefficients. And here again, it's exactly as it was before, but for each of the betas. So the H0 is that beta I equals 0. And the alternative hypothesis is beta I is not equal to 0. And by I just mean any one of these 6 variables. We could also do an upper and lower test. We could also have one-tailed tests, but we'll just do the two-tailed here. And so let's just go through these, and let's just set our alpha equals 0.05. Do we reject the null hypothesis? Yes, this is significant, and this is significant and positive. Yes, this is significant. Yes, significant. Yes, significant. Yes, significant. If we'd set alpha equals 0.01, if we'd been stricter, then this wouldn't be significant. This is kind of marginally significant. And let's look at the individual coefficients. So let's just say this beta. Now, so we'd say that for every increase in floor, as we get higher, then the selling price lowers minus $1,116. This is in the thousands. And again, the further maybe distance being in the entryway is bad. There's a load of people hanging around. For each kind of meter away from the entrance, we go up $917. Now this is like a categorical variable. We have a view 1 or 0, end 1 or 0. And here, this is just the increase with the variable present. So because we only have one variable. So with the view of 1, we have a view that increases the price by 48,000. We have an end apartment. I thought an end apartment was good, but what do I know about this condo complex? Our price is down 23,000. Maybe the end apartments are just not desirable. And furnishing, if it's furnished, it's an average of 7,000. And auction, again, exactly the same 1-0. If it's been at an auction, it tends to be $27,000 cheaper. It kind of goes to show, you know, auctions are people who've been repossessed and maybe the apartments are in bad condition, haven't been looked after properly. Just a little note, you can have categorical variables with more than 2 values. But what would happen is if I had a categorical variable with, say, with 4 values, what SPSS would do is it'd actually give me 3 regression, it'd give me kind of 3 coefficients, and these would would actually be a change from one of the base values. So say, for example, I had 4 different majors with the fear of statistics. The base value would be, say, finance, and then I would get a coefficient for marketing, how different it is from finance, a coefficient from IT, how different it is from finance, and a coefficient from accounting, how different it is from finance. But again, as I said, we're just doing the real basics today on multiple regression. And I already talked about that stuff. So there we go. As I said, I would like to do more, but you guys, I'm not putting this stuff on the exam, so I just wanted to give you a little bit of a taster for multiple regression. I promised you 15 minutes, and I was